Welcome to Fee Channel. In this video, we will learn about the common base configuration of the BJT. Now, if you see, the most common application of the BJT is to use it as an amplifier. That means if we apply some input signal to this BJT, let's say some sine wave, then it will amplify that signal. And whenever we use this BJT as an amplifier, then there are different configurations in which it can be configured, like a common emitter, common base, and the common collector. So in each configuration, one terminal of the BJT is common to both input and the output side. For example, this is the diagram of the common emitter configuration of the BJT. And as you can see here, the emitter terminal is common between the input and the output side. So, in this particular video, we will learn about the common base configuration. So, in case of the common base configuration, this base terminal is common between the input and the output side. That means here, the input is applied between the base and the emitter terminal, and the output is measured between the collector and the base terminal. And as I said in the previous video, whenever we use this BJT as an amplifier, then it is used in the active region. That means the base emitter junction is forward biased, and the collector base junction of this BJT is reverse biased. So for the NPN transistor, the applied voltage should be such that this base emitter junction gets forward biased, and the collector base junction gets reverse biased. And for the NPN transistor, if you see the direction of the currents, then it will look like this. That means here, the emitter current will go away from the transistor, while the base current and the collector current will enter into the transistor. So, if we talk about the PNP transistor, then in case of the PNP transistor, the direction of the currents will get reversed. That means now, the emitter current will enter into the transistor, while the base and the collector current will go away from the transistor. But in any case, if you see, the emitter current is the summation of the base current and the collector current. So, in case of this PNP transistor, the emitter base junction is forward biased, and the base collector junction is reverse biased. Now, in this common base configuration, the behavior of the device can be described by the two characteristics. One is the input characteristics, and the second is output characteristics. And these characteristics are similar to the VI characteristics, which we had seen for the diode. And these characteristics show the behavior of the device when the voltage and the current through the device get changed. So in this case, if you see, this emitter current is the input current, and the voltage between this base and the emitter terminal. That means this voltage VBIE is the input voltage. So, the input characteristics define the relationship between this base emitter voltage and the emitter current for the fixed value of the VCB. And throughout our discussion, we will talk about the NPN. So, if we see the input characteristics of this common base configuration, then it will look like this. So, here there are three curves for the different values of VCB. That means for drawing each curve, the value of VCB has been kept constant. So, if you look at these curves look similar to the forward characteristics of the PN junction diode. Because indeed in this case, if you see, the PN junction on this input side has been forward biased. And due to that, this characteristic looks similar to the forward characteristics of the PN junction diode. Now, one more thing if you observe in this curve, as the value of VCB increases, the curve slightly shifts towards the left-hand side. And at the same time, this emitter current also increases. And the reason is that, as the collector base junction gets more and more reverse biased, the width of the depletion region will increase. And due to that, this base region will get narrower. So now, the less voltage is required to forward bias this emitter base junction. And due to that, the curve shifts a little bit on the left-hand side. Now, from the input characteristics, we can find the input impedance of the device in this particular configuration. So, if we find the slope of this curve, then we can find the input impedance of the device. That means we can say that the input impedance, or the input resistance, is equal to delta VB divided by delta I. And if you see over here, even if there is a small change in the VBA, there will be a huge change in the emitter current. That means from this input characteristic, we can say that in this configuration, the input impedance of the device is very low. And in fact, that is expected because, in the forward bias condition, the resistance of the PN junction diode is very small. And typically, it used to be in the range of ohms. That means we can say that in this common base configuration, the input impedance of the device is very low. So similarly, let's talk about the output characteristics. So here this collector current is the output current. And the voltage between the collector and the base terminal is the output voltage. So this output characteristic defines the relationship between this collector current and collector to the base voltage when the input parameters are kept constant. That means the output characteristics shows for the fixed value of the emitter current. If we change the collector to base voltage, then how the collector current will change. So here the different curves are shown for the different value of the emitter current. And as you can see, as the emitter current increases, the collector current also increases linearly. Now in this curve, there are three regions: the active region, the cutoff region, and the saturation region. So, on by one, let's talk about all these three different regions of operation. So, as you can see, in case of the active region of operation, even if we increase the collector to base voltage, then also the collector almost remains constant. And in this region, the relationship between the collector current and the emitter current can be given as IC equals alpha IE now. Here the emitter current is the input current, and the collector current is the output current. So, the ratio of this collector current to the emitter current gives the current gain of the BJT in this common base configuration. That means in this configuration, even if we increase this reverse bias voltage, then also there is a marginal increase in this collector current. So, we can say that in this region of operation, the collector current behaves like a constant current source. And for the fixed value of emitter current, it is almost independent of the collector to base voltage. And in fact, due to this region is used for the amplification. Because in this region, the collector current only changes with the change in the input current. Then if we talk about the second region, then the second region of operation is the saturation region. So in this region, as we reduce the value of VCB, that means as the collector to base voltage goes negative, then this collector current starts reducing. Because, as we remove this reverse bias between the collector to the base junction, then the electrons which have entered into the base region from the emitter will not able to cross this collector junction. And due to that, this collector current starts reducing. So whenever both emitter base junction and the collector base junctions are forward biased, then the BJT will operate in the saturation region. Then the third region of operation is the cutoff region. That means whenever the emitter current is zero, at that time even if we increase this collector to base voltage, then also the collector current almost remains zero. That means whenever we remove the voltage between the emitter and the base terminal, then the emitter current I will become zero. And under this condition, the collector current I will be almost equal to zero. And in this condition, the only collector current which exists is due to the minority charge carriers. And in other words, it is only due to the reverse saturation current. Because we had seen that the total collector current IC can be given as IC add ICO, where ICO is the reverse saturation current. Now, in the common base configuration when we open this emitter terminal, the reverse saturation current, which is flowing between the collector to base terminal, is known as the ICBO. And this ICBO is similar to the reverse saturation current, which we had seen for the diode. So, due to the improvement in the construction techniques, this reverse saturation current is typically in the nanoampere range, but for the high-power transistors, it is used to be in the range of microamperes. On the other end, if you see the collector current IC, then it used to be in the range of mA. And due to that, in this cutoff region, if you see this graph, the collector current almost appears as now similar to the diode. This reverse saturation current is sensitive to the temperature. That means, as the temperature increases, this reverse saturation current will also increase. So, here the total collector current IC can be given as IC plus ICO. Or if we represent it in terms of the emitter current, then we can say that it is equal to alpha asterisk IE plus ICO. So, this will be the total collector current, which is flowing through the circuit. Alright, so now let's understand briefly how the signal is getting amplified in this common base configuration. And here for the simplicity, the DC biasing voltages are not shown. So let's say Vi is the input voltage which we want to amplify, and the RL is the load resistor. Now, as I said earlier, in this configuration, the input impedance is very low. And typically, it used to be in the range of ohms. So let's say, here the input impedance or the input resistance is equal to 10 ohm. And let's say the input voltage is equal to 5 MV. So we can say that the input current is equal to 5 MV/10 ohm. That is equal to 0.5 M. Now for a moment, if we assume that alpha is equal to 1, in that case, this output current is the same as the input current. Because we know that the collector current IC can be given as alpha times IE. And for a moment, as we assume this alpha is equal to 1, in that case, this IC and IE will be equal. So, under this condition, the output current will be same as the input current. That means the same current will also flow in the output circuitry. Now, for the common base, the output impedance rho is very high. And in fact, that is also evident from the output characteristics. Because if you see over here, in the active region of operation, even if we increase this collector to base voltage, then also the collector current almost remains constant. That means the output resistance, that is delta VCB divided by delta IC, will be very high. And typically, it used to be in the range of hundreds of kiloohm. So, let's say, here the output impedance is equal to 100 kiloohms. And here the value of the load is equal to 1 kiloohm. So, if we want to find the output voltage, VO, then the VO can be given as IO times RL. That is equal to 0.5 MA asterisk 1 K omega. That means the output voltage VO is equal to 0.5 V. Now, here the input voltage is 5 MV, while the output voltage is equal to 500 MV. That means the input signal gets amplified by the factor of 100. Or we can say that here the voltage gain is equal to 100. So, in this way, the signal is getting amplified in this common base configuration. But if you see the current gain, that is the ratio of this collector current to the emitter current, then it is less than 1. That means the current gain for this common base configuration is less than 1, but it provides the voltage gain. And typically, the voltage gain in this configuration varies from 50 to 300. Now, one more thing if you notice over here, the same current is transferred from the input side towards the output side. That means there is a transfer of current from the low resistance circuit to the high resistance, and that is why the BJT was named as a transistor. So that's it for this video. And I hope in this video, you understood the basics of this common base configuration. And in the next video, we will talk about the common emitter configuration. So, if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.